The following is a production of the University of Minnesota.
Today we have with us Professor Arndt, and he started his career in industry, first in rocket propulsion and then in the high-speed marine vehicle field. Since 1967, he's been in academia. Dr. Arndt's major research interests are in the area of fluid mechanics with emphasis on turbulent shear flows, cavitation, aeroacoustics, including jet noise and turbo machinery noise, alternate energy with an emphasis on hydropower and wind energy technology, and aeration technology with a view towards developing cost-effective environmental techniques. He continues his research at the St. Anthony Falls Lab currently, which is with the University of Minnesota, where he's working on wind-turbine aerodynamics and supercavitation. He's a life fellow of ASME, fellow of the American Physical Society, and associate fellow of AIAA. So we welcome Professor Arndt.
Thank you. Oh, okay. I guess I got to use this thing, huh? Okay, well, happy to see some people come here on this crummy afternoon. First thing I'd like to ask is, do you have a background? Does anybody have a background in fluid mechanics? Okay. Okay, so with that in mind, I'll try to go easy on you. Okay. What I want to do today is just kind of give you a little bit of a feel for wind turbine technology and talk a little bit about basic concepts. Talk a little bit about some very early theory. The theory started in 1919. Talk a little bit about rotor aerodynamics, and since you don't have a background in fluid mechanics, we'll just try to lead you through it as painlessly as possible. And talk a little bit about rotor design. And obviously in 2 hours you're not going to become rotor designers, but just to give you a little bit of a flavor for what's involved. And we'll talk a little bit about acoustics and rotor noise, and then a little bit about flow control technology. So with that, we'll start with the first slide. And is this going in and out? Can you hear me okay? Okay. First thing I want to point out is there are actually two types of turbines, the vertical axis turbine and the horizontal axis turbine. And our emphasis is going to be on the horizontal wind turbines. Okay. I don't know if you might have read in the paper, there was a gentleman that has a house on Lake Minnetonka, which is a very high buck area, and he decided to erect one of these. And there's a huge stink in court and everything about that. But I point that out because these vertical axis units show a lot of benefit for being in closed areas. They could be put them on top of an apartment building and so forth. The horizontal axis units are ones that are more prone towards large utilities, and so they're very expensive. For example, you visited the one at Umar Park, and the cost of that was somewhere between $5 and $6 million. Okay? So when we got the DOE grant, the good news was we got an $8 million grant. The bad news was that $5 to $6 million of that was going to go to build the turbine. So there was only $2 to $3 million left for doing research. So let's look a little bit at what we can expect out of a wind turbine. And the first thing we want to look at is, let's look at the power per unit area. Now this is simply 1/2 times the density times the velocity cubed. That is power per unit area that the wind has. Now, if we multiply that power per unit area by the swept area of the rotor, pi r squared, we can say, well, why don't we multiply the power per unit area by the area, and that ought to be the kind of power we could expect. Okay, so we'll do that, and we'll define a coefficient of power, which is simply the power that we get out, normalized with respect to this expectation. Okay, who wants to take a guess at how much we really can get? How many people say better than 90%? How many people say better than 80%? 70%? 60%? Boy, you guys are pessimists. Okay, let's look at what we can really achieve. And it turned out that the low number that we're going to see is not because of any defect in the blades and so forth, but it's just the way the wind turbine operates. And as I said, the answer to these questions were first developed by Betz in 1919, and then a person by the name of Glauert improved that result. So this is the simple analysis that Betz made. And the first thing we'll look at is, let's look at a typical thing. And you notice here that we have a certain wind speed, but the wind has to slow down as it goes through the rotor. So that means that if we looked at the area that is actually encompassing the wind, you can see it starts with a cross-sectional area like so, expands to this pi r squared that we were talking about, and then actually expands further. So if we start upstream, we have a velocity, say, u, and right at the rotor plane, we have a velocity v, let's say, and further downstream, we have a velocity u2. So the first thing we can look at is let's calculate the thrust that would be on that rotor. So that we have an upstream pressure of P1 and a downstream pressure of P2, and we multiply that difference in pressure by a cross-sectional area, which in this case is that pi r squared we were talking about, and we can come up with a simple equation here that the thrust is equal to the product of density, cross-sectional area, the velocity v here, and the difference between the velocity upstream and the velocity downstream. Okay, so that gives us one equation, but you notice here that we got some unknowns because we don't know what v and u2 are. So what we'll do is we'll write a Bernoulli equation. And with a Bernoulli equation, we can start with one upstream, and we'll say that 1/2 rho u squared plus p atmospheric, because we'll assume that we're at atmospheric pressure here, is equal to 1/2 rho v squared plus p1 for this point. Okay. Now you can't write a Bernoulli equation across the rotor, but you can start at the back end of the rotor and write another Bernoulli equation. So we'll start there, and we have upstream at the bottom end here, we have 1/2 rho u2 squared plus p atmospheric, and right here at the rotor plane, we have 1/2 rho v squared plus p2. So combining all of this, we can get that the thrust is equal to rho times the square of the upstream velocity minus the square of the downstream velocity times this pi r squared. Okay, so we now can play with this a little bit. We have two equations that we've derived. One is for simple momentum, which is rho av, the difference of upstream and downstream velocity, and then this equation we just derived using the Bernoulli equation. So if we eliminate thrust between those two equations, we can calculate that the velocity that goes through the rotor plane is the average of the upstream velocity and the downstream velocity. So what happens is the wind slows down to a velocity v, and then it slows down even further before it exits out of the whole control volume here. Okay. So now, what we'll do next is, and you know what's really nice is that there really isn't any high-powered math here. But I always am fascinated by some of these old characters that could really, get down to the nitty-gritty with a simple equation and get a very interesting result. And in this case, we said, okay, we've got these two equations, and let's see what we can do with them. So let's take the difference between the upstream velocity and the velocity going through the rotor plane, and say that's equal to some quantity a times u. If we go up into this equation here, we'll see that the difference between the upstream and the downstream velocity is 2au. Now, if we take the power, want to calculate the power, that would be equal to the thrust at the rotor plane times the velocity going through the rotor plane. We can just put all the numbers in here, and you can see that we finally get up a result that's 1/2 rho au cubed. That's what we figured we ought to be able to get. That's the power per unit area. Power multiplied by unit area A. And you notice that we have this quantity 4A, 1 minus A. That's the quantity 1 minus A squared. Okay? Now, if we wanted to calculate what the maximum C sub P will be, we can divide through by 1/2 rho AU cubed. This is the definition we used on the previous slide. And we get that the power coefficient involves this quantity A, 4A, 1 minus A quantity squared. Okay, what do we do next? When in doubt, you differentiate, right? So you differentiate here. And so you take the differential of C sub P with respect to A and set that equal to 0. And that will give us the maximum value of that C sub P for that value A. Okay? So we do that, and it turns out that A is equal to 1/3. So if we put 1/3 into this equation, it turns out that the maximum value of the power coefficient is a little under 6/10. So all the pessimists in the audience were close to correct. Okay? So also, we'll use this later on, but we can also calculate the thrust coefficient as just simply the thrust divided by 1/2 rho U squared times A, and that's just equal to 4A, 1 minus A. We'll use that little formula a little bit later on. Okay, so that's fine. Let's just use linear momentum. And on the basis of linear momentum, he came up with that calculation of the maximum possible power coefficient would be a little under 6/10. But it took quite a while. Let's see, 1919 and 1935. So 16 years later, Glauert came along and said, well, look, you still have another tool in your toolkit because you can conserve linear momentum. But since this thing is turning and there's a torque involved and so forth, we can also use conservation of angular momentum. And by using conservation of angular momentum, we can get another equation here. So this implies that if a rotor is turning, there has to be an equal and opposite rotational component to conserve momentum, angular momentum. And that's shown here. Here we have actually wind tunnel measurements made with a 3-bladed rotor, a model rotor. And you can see that the blades are turning this way, and there's a wake component that's rotating equal and opposite in the other direction. So Glauert used that piece of information. I won't go into the gory details. But what he found then was that this upper limit that Betz had calculated up here actually needs to be modified like this. And the modification is that we only get that maximum of the Betz limit when this specific speed or tip speed ratio is quite large. You can see. So you can see when this tip speed ratio is low, you don't get even that. You don't even get the 6/10. Okay. Now this tip speed ratio is pretty important, and you can see here that if you were a designer now and you want to get a lot of bang for your buck, what are you going to do with tip speed ratio in your design? Say again? Right, make it high. I mean, there are limitations on how high, but let's just take a simple example. Let's say the tip speed ratio was 5 for the U of M turbine. I think it might be 5 or 6, but let's take 5. Okay, so let's say we got a wind of 10 meters per second. Okay, and we want to have a tip speed ratio of 5. So that means that omega R would be 5 times that amount, 5 times 10, or 50 meters per second. Does somebody know what 50 meters per second is? It's a very easy number to remember. All you got to do is multiply by 2 and you get it in knots. Okay? So 50 meters per second is 100 knots. And 100 knots is like about 120 miles an hour. So it's... if you see these wind pills, they're turning really slow, but the tip speed is very, very high because they're huge. The rotor diameter on that turbine you saw down in down at the U at Umore Park, that's got a 98 meter radius, 98 meter diameter. So that's a rotating football field, 100 yards to a football field. So those things are huge. They don't look huge when you look at them from afar, but when you get up, I guess you all got up close and personal with it, and you can see how large they are. So the important point here is you can see that as we go up and modernize our design, we want to start shooting for higher tip speeds here. So, how should we get that energy out of the wind? Should we just use drag? If you blow on something, you can make it move. Or should we use lift? Well, let's start with drag. So let's have a simple machine here. Let's consider this to be a vertical machine. So this is rotating around a vertical axis. And let's just break this down in the simplest form here so that we have just this paddle here is doing work. This one's not doing work. And we have the wind relative to the paddle is equal to the velocity u minus the tip speed, which is omega r. Okay, everybody see that? So the paddle is trying to move away from the wind, and so the velocity that the paddle is actually seeing is the wind velocity minus omega r. Is that clear to everybody? Okay, so now what we want to do is calculate the drag. And the drag is 1/2 times coefficient of drag times rho times the relative velocity squared times the cross-sectional area of the paddle. And if we want to calculate the power, all you got to do is take the drag times the tip speed, omega r, and that'll be the amount of power that's coming out. Okay? And so if we go through the motions here, you can see that we get 1/2 c sub d rho a. The relative velocity is u over omega r squared. Then you have to multiply by omega r again, divide through by u cubed to get it in this form. And you can see now that also what's coming up is this tip speed ratio. Okay. Now, if we define the power coefficient just by dividing through by 1/2, and what we're going to do here, it's a little trick. We're going to use the relative area here to be 2 times the area of the paddle. So we're going to take into account this area and that area. It's just definition. Okay. So when we do that, we get this simple form for the power coefficient, and this maximizes when the tip speed ratio was only 1/3. Now we looked at the other thing there and we saw that we needed high tip speed ratios. So what is this telling you right away? That if you try to use drag for it, it would be optimal at very low tip speeds, but the very low tip speeds don't give you a very good efficiency. Is that correct? So you can see that drag doesn't make much sense. So what you do instead, we're going to use lift, and lift, the relative velocity will be the product of velocity squared and the tip speed squared, the square root of that. And you can see that now, the relative velocity we're operating at is greater than the tip speed, greater than the free stream velocity. And that's illustrated here. So is there any sailors here? Anybody sailed a boat or sailed an ice boat? Or you've all been too busy studying, huh? But if you look at an ice boat, for example, you can go out. Ice boat's a nice example because if you get a nice smooth ice, you got very little friction, and you could go out and get maybe 5-6 times the speed of the wind. And you say, well, how the heck can you do that? And it's very simple here. If you look at this, you have a relative wind here. In this case, for the wind turbine, we have the wind turbine is rotating with a velocity, and that velocity is omega r, which is tip speed. So relative to the blade, we have a component omega r, and then coming in normal to the rotor is the velocity 1 minus a times u. Remember that going through the rotor, the velocity was 1 minus a times u. So if we look at adding up these vectors, we see we have a relative wind that is in that direction. And it turns out that for lift, the lift is normal to the relative wind. So you can see you get a component of lift here. And if we take the component that's in the plane of the rotor, that's what's giving you a torque. Okay? Now notice there's a couple of other things here. First thing is you see that we have a angle here, phi, and that phi is made up of two pieces here. We have a piece here called beta. That will be the pitch of the rotor. So you're going to see right away that since as we go to different radii within that rotor, clearly this number is getting smaller and smaller as we go down the rotor. This number is staying constant. So you can see that the beta has to increase. And that's why when you look at a rotor, it has a twist to it. Okay? And another important point here is that this phi is the whole story. The beta is the twist or the pitch that the blade has at any particular radius r, and the other part is angle of attack. So it turns out, we'll see in a moment here, that angle of attack governs how well that foil is going to perform. So that there's an optimal angle of attack that the foil will perform the best at, and we'll see that in a moment here. So if we look at a typical piece of a foil, we can talk about it having a chord length, C. It's at some angle of attack alpha, and it's got some relative velocity coming in. And we can talk about a lift coefficient, and since this is in two-dimensional form, we'll talk about the lift per unit span is given by the lift per unit span normalized with respect to 1/2 rho u squared times chord length. So that lift coefficient is just another normalized number. And the amount of C sub L you have is governed by the angle of attack it has. Okay? So I'm not going to make you aerodynamicists by the end of the hour here. So if we look at some data here, first thing to notice is this happens to be a foil that was developed at Delft. That's the D in there. Delft is a university in Holland. And you can understand why they might be pretty good at making windmills. They've been making them for centuries. This particular shape was optimized for windmill operation. And the first thing you look at, you can see here that as you change angle of attack, the lift coefficient increases. But if you keep increasing it, it stalls. So what happens is you go up and up and up and up, and pretty soon the flow doesn't stay attached to the foil anymore, and the lift drops off. Any pilots here? No pilots as well. Usually you get one or two pilots. But okay, well, if you stall your airplane, you can feel it right away. I mean, you can just be pulling up on the elevator, and it's going slower and slower and slower, and then finally it stalls, and it's just like being in an elevator. It just goes down. Then what you got to do to recover is push on the elevator and hit the throttle, but that's something else. Okay, so now that shows we can get this stall here. Another interesting feature here is there's two cases here, and they were doing some stuff with leading edge tape, and we won't worry about that. But notice here that this is a plot of drag coefficient. That's simply the drag normalized in the same way as the lift coefficient. And you can see here that for this particular foil, we have a pretty low drag coefficient over a wide range of lift. So that's a good thing to have if you're in a wind. Why would you care about that? Is the wind velocity always identically the same? As you know, it's all over the place, and so you have to be able to design a wind turbine that can operate over a range of velocities. So it's very important to have a foil section that is good over a range of lift coefficient, and lift coefficient is changed by the velocity. Okay? Okay, now, up until now, Betz used a theory that he took the rotor here and he assumed that rotor was just an infinite number of blades. So that, in other words, the entire rotor was covered with blades. Now, in the real world, you have something like this. So, for example, most of the horizontal wind turbines have 3 blades. And so now you've got to back off again and not do your momentum analysis on the whole area. But what we'll do is we'll calculate differential forces that relate to this differential area here. So that we can take a differential area at any radius r, multiply that by dr, and the differential area there is simply 2 pi r dr. This is classical stuff you've done 5 zillion times in class. So now what we're going to do is we use the same picture. Other than that, we still have an inlet velocity of u. We have a velocity going through the rotor plane of u1 minus a, and on the downstream end we have a velocity exiting the control volume with u1 minus 2a. Okay. So now this looks busy, but it's not really very busy. Okay. So from before, we had calculated what the torque was over the entire area. Now what we're going to do is we're going to just take a differential torque over that cross-sectional area and then multiply that by the integrate over the entire rotor area to get the total result. So we start out with a differential force here, rho u squared, and this is 4a, 1 minus a. This came from the Betz calculation. Instead of area here now, pi r squared, we'll use pi r dr. So we have a differential force, and we're going to have to integrate over the rotor to get the total force. Okay, and so we do this here. We already calculated that phi, the angle phi here, was equal to alpha plus beta. Alpha is the angle of attack that we want to have that rotor blade at, and beta is the pitch that we need to have to give it that angle of attack. We can just use the geometry of the situation here, get the tan phi is equal to 1 minus a over a localized tip speed ratio. So rather than omega times capital R, this is the value at any radius r. So there's just omega r over u. Okay. At the same time, we can also calculate sine phi, and from that we can then get that the velocity, the relative velocity here, is equal to 1 minus a over u times sine phi. So we can now go ahead and write another equation. And for this one, we're going to say that now that differential force that we see there isn't pressure uniformly over that entire area, but it's given now by the number of blades times the lift on that section of foil, 1/2 rho VR squared times the lift coefficient times dr. That gives us the differential force there. And the cosine phi is just to take into account, we just want the component that's in the rotor plane. Okay? So that gives us another equation here, and that's the airfoil equation. So we have a Betz equation and an airfoil equation. And what we're going to do is we figured out from before A equal 1/3 gives us a good efficiency. So we'll put that in there, and we end up with an equation that looks like this. And it looks complicated, but it really isn't. It's given this angle sine phi here, cosine phi here, lift coefficient, and B is the number of blades. So it's really quite simple. Okay, so now we can then just simplify here, and we get this simple equation here. And keep in mind that the tan of that angle phi is just given by 2 over 3 times that local tip speed ratio. And we can then calculate that phi is just the angle of this. We can then substitute that in, and we just get this simple equation here. So we have this equation, which gives us the chord length, and we can see here that this lambda r is equal to the tip speed ratio divided by I got this wrong here. Okay. Oh, r. Okay. R over capital R. That's where it should. From over here at this angle, it looked like it was R prime or something, but it's just so. In other words, you have a tip speed ratio that's given by omega capital R over u, and what you want is a localized value, which is simply omega little r over u, and so this value is just equal to the tip speed ratio divided by that. So you can see here now that if you are going to be a designer, you could start to play around with different tip speed ratios and so forth to see what you get. Okay? Now you're going to have a homework problem doing this, so we're going to actually show you how to make this calculation as a homework problem so that you can see those equations are very simple. And what you can do then, in this case, we're going to assume those equations are based on assuming A is 1/3. We're ignoring the wake rotation, which was considered by Glauert. We're going to take a tip speed ratio of 7, and this is a relatively small turbine. It's only 5 meters in radius, so it's a 10-meter diameter turbine. And we're going to assume 3 blades, and we're going to assume that the optimum angle of attack is 7 degrees, and we'll assume the lift coefficient to be 1. And you can just use those equations, get yourself a little chart, just make those calculations here, and then you can actually calculate the chord here in terms of normalized radius. Okay? So at the tip of the rotor, that value is 1, and then at the hub, it's equal to 0. And you can see here that the chord length of the foil is relatively small, and it gets wider and wider as you go down. So when you look at the blades, you can see that they got that kind of a shape that is tapered, so that at the top you've got the relatively small chord, and then getting to the hub, it's a much larger chord. And also from that calculation, you can calculate what the twist of that blade will have to be, and that's plotted there. So you have a homework problem that will show you how to do that. Okay. Now, we'll go back to Glauert, and we'll say, okay, well, let's consider the conservation of angular momentum. Okay. Now, I'm not going to belabor this point here because it gets a little complicated, but the basic thing is that the torque on the rotor is given by the mass flow times the angular momentum per unit mass. Okay? So this is the flux of angular momentum, which we write here. Okay? And now you can see that we get one additional term in here. We have the A that we dealt with before, but we have another term here which is called A prime. And A prime is nothing more than getting an equation for this V theta. We say that V theta is equal to 2A prime times omega r. So you've got that other little parameter there, A prime. Okay? And as before, the velocity going through the rotor plane is 1 minus A times the upstream velocity. So we can write this all out here and get this equation. We'll call this equation 1. Now, we can go, as before, we can calculate the lift on the blade, and we can keep in mind now that the lift on the blade gives a force in the rotor plane that's gotten by multiplying by sine of the angle. Remember, to get the force in normal to the plane, we multiply by cosine of that angle phi. So we calculate the torque now, and the torque involves the lift on the blade, differential lift on the blade, times the sine of the angle, and the radius at that point. So you got a force times the radius gives you a torque. Then you just have to integrate that over the whole rotor plane. Okay? And that boils down to this equation here. And from before, we can look at the V sub r times sine theta here. And that's this term here times there. And come up with the fact that V sub r is equal to U 1 minus A over sine phi. This is just playing around with trigonometry here. So we get an equation for the torque now that looks like this, and it involves yet again another term. And that term is the number of blades times the chord length divided by 2 pi r. And that means that it's a solidity value at each cross-sectional area, so that you start out at the top, you have a certain solidity, and the solidity becomes greater as we move towards the hub. Okay? Okay, now this looks complicated, but the bottom line is just simply that you have a torque equation that involves this local solidity, the free upstream velocity, and this parameter A and sine phi. And then we have another one that we got from conservation of angular momentum, is this. So notice what we're doing now. We got an equation for torque from conservation of angular momentum. We got an equation for torque by just calculating the force on the blade times the radius at that particular point. So now we can take those two equations and manipulate them. And so we can equate that and do this. And we can then go back and use conservation of angular momentum to get another equation. And so this equation is a conservation of angular momentum. This equation is conservation of momentum. And with some manipulation, we get down to this form here. Now this looks complicated, and the way it is, because you have to think here now that you have these three equations, and what we can do is you can either numerically solve this set of equations, or you can plot them. Okay. Now I'm going to kind of pull the wool over your eyes and show you what it means to plot it. So let's take this parameter here, and let's see how that parameter would change as a function of angle of attack for different values of phi. So we can plot, for example, the lift coefficient versus angle of attack, and the angle of attack varies so that you have the twist plus the angle of attack is that phi. So you make a plot of this parameter here. That's this guy here. And you know that the relationship between lift coefficient on the blade and angle of attack is given by experimental data. Now, this is not a one-shot deal here. Okay? So you really have to manipulate a little bit, pick different angles of attack, calculate a phi, and get it to the point. So you can see here, when this equation goes with this one, this says that for this situation here, you should be operating at this angle of attack alpha. And that you can see that that is well within the range of where the foil is useful. Okay. Okay, now, if we look at the results of doing this, and I did not give you a homework problem on that one, okay? I only gave you a simple one on the, just balancing linear momentum. If we look now at this problem, we can talk about a solidity. The overall solidity is the number of blades times the planned form area of the blades divided by pi r squared, okay? So if you had a certain number of blades, let's say 3, and the area of the blades is so much, divide that by pi r squared, that gives you a relative, you can kind of look at it this way. If you looked at the rotor, this would tell you how much daylight you could see. Okay? Because you've got the blades there, and then where there aren't any blades, there's daylight. Okay? And you can see that if I put more blades on there, then I see less daylight. Okay? Okay, now I can talk about a lift coefficient. The one we were dealing with was the lift per unit span. That was a two-dimensional one, and that was defined in this way here. Now we can also talk about a lift coefficient for the entire blade. So that would be the total lift that the blade produces, and for that we'll normalize with respect to the area of the blade. And for a simple case here, we'll just assume that those two lift coefficients are equal. And there's a little complication in doing that, but it's not a bad assumption. Okay. Now, if we now just take the product of the this parameter here times the lift coefficient and plot that as a function of a tip speed ratio, notice that as the solidity gets smaller, the tip speed ratio gets higher. So that if you look at a modern wind turbine that has a relatively high tip speed ratio, the blades are quite slender. But if you had a real old-fashioned turbine, you'd have real fat blades and it would be turning very slowly. But modern turbines have relatively slender blades turning relatively quickly, as you can see from this plot here. Now, another thing that comes into play here is that how many people have had any structural? Anybody had structures? Okay, you remember from Physics 1 what a cantilever was, right? Okay, and you remember that if you have a cantilever, it's fixed at one end, and if you push on it over here, it creates a moment. And the more this thing is cantilevered, the more moment you have here. And the more moment you have here, the more stress you have. So in a wind turbine, think about that. Like, for example, the one down at Umore, that turbine is roughly 100 meters in diameter. It's actually 98. And so it's got a radius of roughly 50 meters. Okay? And that is cantilevered at the hub. So you got all this wind pushing on that turbine, and it's creating quite a force, quite a moment. And so you have to accommodate that. And the way that's done is you make the blade thicker and thicker as you get closer to the hub. Because the little piece out in here is not seeing as much moment as when you get down to the hub. Then it's got a much more moment, so you got to accommodate that. And so if you would look carefully at those blades, I know it would be much easier to see if you saw a blade laying on the ground, but basically at the hub, the blade is quite thick. In fact, in some turbines, they just make this a cylinder down at the bottom here. They just have it perfectly cylindrical. And then as we move upstream, up to the tip, it gets more and more slender. Okay? Everybody see that? Okay, next thing is, can we just go forever? Just, I mean, if a tornado hits, we can just go happily on our way and collect more and more energy? What do you think? No, obviously there's an upper limit to this, and in the case of most turbines, they have something that looks like this, and this is what a very important parameter that engineers play with. What we plot here is the power that this particular turbine generates as a function of wind speed. And then you get to a certain point here where that's the maximum power that you've designed for, and so you don't want it to produce more power than that. So then you got two options here. Nowadays, you use what's called pitch control. How many people have been on an airplane that's a turboprop? Okay, so what happens when it lands? It makes a heck of a racket. Well, why is it making a heck of a racket? Anybody know? Well, the pilot is changing the pitch and actually putting it into reverse thrust to slow the plane down. So he changes the pitch, and you can hear that right away. So what's done here is as the power exceeds a certain value, you just simply change the pitch so that it doesn't keep producing more and more power. Now, another way to do it would be to design this thing to stall. Okay? Now, look how that would work. Look at this little diagram here. Okay? And let's say that we hold the pitch constant. Okay? So we're holding the pitch of the rotor constant, and we increase the wind speed. Oops, didn't mean to do that. Okay? So if we increase the wind speed, that means that this vector gets larger. What happens to phi? We're keeping omega r constant. Okay? We're keeping beta constant. What happens to the angle of attack of the foil? Phi's getting larger, beta's staying the same. Phi minus beta is equal to the angle of attack. So the angle of attack is getting larger and larger. And what do we learn about what happens if the angle of attack gets too large? It stalls. And so it stops producing power. So in the old days, they would design this in such a way that the blade would stall at the point of maximum power output, desirable power output. Okay? Any questions on that? Okay, now, there's a lot of other little things. I mean, you're certainly not going to be an aerodynamicist after all, as I haven't been an aerodynamicist in 60 years. There's a lot of other interesting facets to this problem. And one is a so-called tip vortex effect. Here's a a model rotor. It's actually a very large rotor, and it's actually in a very large wind tunnel at NASA Ames. And they made visual the flow at the tip with smoke. And you can see that you get this helical motion here. So you basically have a tip vortex, since the blade is rotating and there's flow going in there, it creates a helix. Okay? So this has an effect on the rotor. And we'll look at that in a moment. Now you see the same thing on a propeller. Same thing here. The propeller tip vortex is made visual. There was just a humid day, and so humidity came out of solution here and made the tip vortex visual, as you can see here. Now you would say that what's the difference between the tip vortex, which I've illustrated over here. So what we've done now is we've just simply taken a slice normal to the rotor plane, and you can see then that you cut this helical vortex here, and you can see a couple of things that are happening here. That is, you can see that the vortex is actually growing in size and thickness as it moves downstream. But we can look also at a visualization of flow from a propeller. Now the difference here is that the flow is slowing down as it goes through the windmill. So the flow leaving the downstream end of the windmill is slower than upstream, okay? Because it's taking power out. Okay, now with a propeller, you're doing just the opposite. What are you doing? You're putting power in, okay? So when you're putting power in, this means that the flow has to be accelerating. And so in this case here, you can see this is made visual by a special technique called particle imaging velocimetry. And you can see the same thing here. Here's the same helical vortex structure visualized by looking at it in a plane normal to the rotor. Okay? But you can see there is a subtle difference in the tip vortex structure between the two. So one has to keep that in mind in making calculations, and you will not be asked to make any of those calculations. But the tip vortex is an interesting problem. Incidentally, I was on one flight going into San Diego a year ago, and all of a sudden we were flying along, and there was a huge bang. I mean, like a bang, like somebody just hit the plane with a hammer. And I got the best explanation from a pilot of it being a tip vortex. And what happens is that if you look at a tip vortex, you have a wing here. Now, a wing has a higher pressure on the bottom and a lower pressure on the top. That's what gives it a lift. So the high pressure at the tip swings around. It goes from the bottom of the tip to the top of the tip, and it creates a motion, or a vortex motion. And that's illustrated here. So you can see in this end, we have rotation in this direction. And over on the other tip, we have rotation in that direction. Okay? Now, how many people have noticed geese? Okay. You know, I haven't figured this out yet, but geese seem to be smarter than penguins, because penguins, not penguins, got a mental block here for a minute, but another kind of bird just flies one behind the other. What a goose does is does this, and if you look carefully, you'll notice that they change position, so that you'll start out with one goose. So the goose in the front here, he's flying along, and he's creating a tip vortex that looks like that. So that means the next goose will fly in the upwind of that. So he gets a free ride, so to speak. Okay, and then the next goose is out here, getting a free ride from that goose. So you get this V formation with each one of these geese flying in the tip vortex structure of the one just upstream of him. Okay, so now what would be a stupid place to be? Well, a stupid place would be to be right behind, because if we look at this here, at any particular position along the span, we have a downwash. Okay, so it's not very bright to be flying right behind a goose, but you'd be much smarter to fly off up on the wingtip of the goose, because then you'll get a little bit of help. Okay? And you can see that's illustrated here, so you have a downwash anywhere. Well, this downwash creates a little bit of a problem here. I've sketched that over here. Now, let's say here is this foil here at some angle of attack. And notice here that I have a velocity that would look like this, but because of the downwash, this velocity and that velocity add up to get a relative velocity that you can see is at an angle of attack. So the blade is seeing an induced angle of attack, alpha I. Thinks it's going straight and horizontal, but it's not. The relative velocity is at this angle, alpha I. That means then that if I'm holding this blade at an angle alpha here, it really isn't getting the benefit of that angle alpha because alpha I is subtracting from it. So the blade is actually seeing less of an angle of attack than he thinks he is doing. And that creates another loss factor in an airplane that's called induced drag. So that needs to be taken into account. So to make a long story short here, and you're probably saying it was too damn long as it is, but if we look at the simple things that we're doing here, we're saying we got a lot of things to do, a lot of things to calculate. How many people believe that we can just calculate this all? Just take these equations, go home, design the wind turbine, and we'll be okay. Well, actually now the answer is you're pretty close that you could do that, but not perfectly yet. 20 years ago, 30 years ago, you wouldn't even have a ghost of a chance. Okay. The point I'm making is that we need to do some experiments to really pin down what all these complex aerodynamics are. And so you saw, did you get to visit St. Anthony Falls? I forgot to look. Did you visit the lab? Oh, probably not, because we're under construction, so it's difficult to visit. Anyway, the lab has a very large wind tunnel. Okay, and a wind tunnel is nothing more than a way of recirculating the flow around, and we have a test section here that we can put model wind turbines in there and make measurements. Okay, so one of the things that we could look at, for example, is if we look at the problem that we have in the field, the wind that's at the ground level is much lower in speed than the wind way up high. I'm sure you've driven into campus some days and the wind is relatively low at the ground level, but you look up at a building and you see the flags are waving around like mad. So you've got a huge variation in velocity. And that has a significant impact here, because this means then that if I look at the load that's on that blade, it has a different load at top dead center than it does at bottom dead center, because the net velocity on the blade is less at the lower level than at the top level. So this creates a dilemma here, because you have a force which on each blade varies as the blade moves around. So it's got a high force up at top dead center and the lowest force at bottom dead center. Now, to study those kinds of things, we can actually create the same velocity variation in the wind tunnel. So we can get a situation where we have a velocity that's high at the top dead center and low, relatively low at bottom dead center. That's illustrated here. And you can see that if I look, for example, just at turbulence intensity, because of the higher wind speed here, the turbulence is much, much higher on the top than it is on the bottom. And this makes things difficult because you are now dealing with unsteady loads. The reason they're unsteady is that you're at top dead center, bottom dead center, top dead center, bottom dead center. So you got an unsteady force that's going at the turbine RPM. So another point here is that I think you all realize we just talked about the goose. Well, you have a kind of a similar problem with wind turbines. The one you saw at UMOR is only one turbine. But if you look, typically you have a wind farm, so you have a large number of turbines that are positioned, and the question is, what's the best way to position them? And this is illustrated here, that if I looked at two cases here, let's say I put the wind bill, would stagger these, okay? You can see that just looking at the colors here, there's not that big a impact on each one. In other words, you don't see the wake changing that much. There is some turbulence there, but you can see that it's nowhere near if I stagger them right in line with each other. Okay, so then I have one turbine, the upstream turbine is making a lot of turbulence, and it's smacked right into the next one, and the next one, and the next one. And you can see that the difference is incredible here. And what you can do here is actually figure out what is the difference in the amount of power, total power generated by that wind farm in various alignments. So what we plotted here was we put these turbines in, and we just measure the speed that they turn at. And what we have plotted here is the speed that each turbine's rotating at relative to the speed that the first one's rotating at, okay? So that starts with 1 here. Now you can see with the staggered one, it doesn't drop, the next one units down don't drop off in speed as quickly as they do if you just one right behind the other. Okay. Now there's a lot of issues with that because the wind is not always blowing in the same direction, but that's another thing to consider here. So we could actually calculate. I won't go through the math here, but all you need to do is, it turns out that these units turn at the same tip speed ratio. So since they're turning at the same tip speed ratio, the difference in power is related to the rotational speed. Okay, and so we can calculate a change in power depending on this ratio of rotational speed from upstream to one of the downstream ones. And we can calculate that you get 15% less power with them being aligned behind each other as staggering them. So that's a huge amount. Keep in mind that each one of those is $5 million or so, and you might have, I forget what the numbers are getting up to now, but you might have 30, 40, maybe more. So you got a huge investment there. And if you're getting 15% less on your investment, that's pretty significant. So some of the things that we've tried at the U in trying to improve conditions is look at different things that we can do to make the turbines run better. Okay? One idea is that we know that when you have flow over a surface, you have skin friction. So is there some way we can improve that? And it turns out that actually there's a product that actually is manufactured by 3M, but they haven't been able to really sell it to anybody yet. They did a test. They actually put this riblet film, and I'll show a picture of it. You cannot tell that these serrations are less than 100 microns. So you can't really see it. If I gave you the tape, you couldn't tell whether it was the active side or the inactive side. You just have to run your nail over it to see that. But putting that tape on there can reduce the skin friction by 5-6%. Okay, so they actually tested this. They took a airliner that was flying between London and Hong Kong over and over again, and they got about a 6% reduction in fuel consumption. 6% is humongous. If you read the paper, you know, the airlines are always telling you how fuel cost is their major cost. And so 6% reduction in that is dramatic. Now, the person that invented this idea was a German engineer by the name of Beschert. And he made some tests, and what he did is he made tests in a channel. And again, since you haven't had fluid mechanics, it's a little difficult to explain it completely. But if you have flow in a channel that's fully developed, then the difference between the pressure upstream and the pressure downstream in that channel has to be equated simply to the skin friction. So you've got the skin friction over the area is equal to that pressure difference times the cross-sectional area. So if you have fully developed channel flow where the velocity profile is the same at the inlet and the outlet, you can easily measure the skin friction drag. Just measure the drop in pressure, and that's the skin friction. Now, what was done was a lot of tests were made, and these tests were made with over a range of conditions here, and this is a non-dimensional spacing here, and I thought I had the formula here, but I guess I don't. I do on the next slide. Okay, so all this is a plot of the reduction in skin friction as a function of non-dimensional spacing of those riblets. Okay, and you can see that there's an optimal value, that non-dimensional value should be somewhere of the order of 12 or so. Okay. And so that would mean that if you could design select this to be in that range, then it would work. Now the problem is that on a rotor, the skin friction varies over the whole rotor, so you don't know how to exactly do that, so you have to do some more research. And so what's done here in our wind tunnel is you can see that we have a dummy foil here, and this foil is representative of what the rotors would be at the tip. It's 1 meter in chord length. It's a quite large foil. And we put riblet film on there, and you can see here is the riblet film. That's the riblet film right there. And then if you blow it up, you could see the actual serrations, but you'd have to use a high power microscope to see those serrations. And we have methods of measuring the skin friction over the whole chord that way, because we don't have the option now of measuring the pressure difference because the skin friction is varying over the foil. So we did a lot of experiments. We used the riblets of various geometries here and changed the spacing and the height and so forth. And then we also looked at, do we need to cover the whole foil, or could we get by with only covering a portion of the foil? So we did some with partial coverage to see what that would do. And the first thing we did was we just looked at the skin friction. And again, all these coefficients are the same. They're all, in this case, the skin friction coefficient is simply the shear stress divided by 1/2 rho u squared, where u is the maximum velocity. Okay. And if we look at this plot here, that varies with a parameter called Reynolds number. And what we notice here is that we could put various riblets on there, and we do see drag reduction. Okay, so that was positive. Okay, so now we'll look at the effect of that. And what we do is, if we looked at this drag polar here, the lift coefficient versus drag, if we just plot it with this kind of a scale, you don't see much of a difference except the very large values of spacing or height make things worse. You get more drag. But if you blow this up now, you can see here that for the smaller values of the riblet film, you do get significant drag reduction, so up to about 5-6%. If you have serrations that are too big, then you start to lose. Okay? So there's an optimal in there. So we home in on the optimal, and we found that for this particular case, that we can make some calculations to see if we take the optimal, back up here a minute, you can see here in this particular case, it looks like something like the 100 micron is the best value. Okay, so we use that 100 micron film, and what we need to do is calculate where is the flow Trying to see if I can get around this without. Okay, so if you look at flow on anything, the flow initially starts out at the leading edge being laminar. In other words, there's no turbulence in the boundary layer. But as you get to a certain point, it starts to become turbulent. Okay, so that means that in our particular case, this serrations only work where the boundary layer is turbulent. So we actually did some calculations to calculate for different values of lift coefficient where the flow transitions to turbulence, so that we have for the upper surface and we have where it is for the lower surface. And so what we can do then is say, look, let's only put the riblet film where it's doing work. In other words, only put it where the boundary layer is turbulent. So for the upper surface, we start about here at about 40%. And for the lower surface, we only cover last 30%. And so this will give us a relatively good performance, not perfect, but you can see here that just doing partial coverage, we do pretty good. So, and this stuff costs a lot of money. It's not cheap. That's why 3M is making it. And so it requires, if we just use partial coverage, we have a good chance of getting a reduced cost and getting some effectiveness. So the last thing to say is, okay, so we calculated that and we found out, for example, our experiments on the 1 meter foil, 100 micron riblet film worked the best. Would it work the best on a 1/4 meter foil or on a 2 meter foil? What's your guess? I think you rationalize that it ought to be different size riblet film depending on what the chord length of the foil is. Okay, so what we need to do is figure out some way of doing that, and the way that's done is we work with a parameter here. This is a normalized length. So what some numerical simulations show that if we take the area between the grooves, okay, and multiply that area by something called shear velocity, which is nothing more than the square root of the shear divided by rho, and divide by kinematic viscosity, that, if you work that out, that's a normalized length. It has no units, okay? And so you can see that this would give us a normalized length, and what we want to do now is see how that normalized length will vary. So the hard thing here is that we really should be using the actual shear stress, but instead we'll just use the overall drag coefficient. So we just simply say that the shear velocity normalized with respect to velocity is just the square root of 1/2 the drag coefficient, and just trust me, it's correct. So I calculate this normalized length here as being related to the velocity and this characteristic length of the serrations divided by kinematic viscosity and the square root of the optimal drag coefficient. And we find out that this normalized length ought to be 10. So now we know that normalized length has to be 10. We can calculate what that means for various values of the riblet size normalized with respect to the chord length. Okay, so we can just simply divide through by chord length here and calculate how we maintain this value of 10, and it turns out to be relatively simple. So if we take the riblet size divided by the chord length, that's approximately 15 over the square root of the drag coefficient and 1 over the Reynolds number. So you have a simple little way of looking at things here. Okay, well, how well does this work? And I won't go into the details here, but it turns out that if you get a 6% drag reduction on the foil, that doesn't translate into a 6% improvement in the power coefficient. And so you have to use a formula here that was derived that involves that. And the parameter that's important here is the drag to lift ratio that the foil had before you improved it. And I won't go into the details here, but for example, if I started with a drag to lift ratio of 1/20th and did a 5% improvement, that would bring it down to a drag to lift ratio of 0.0475. And now, if I look at what the improvement in the power coefficient is, the various values of the tip speed ratio, you can see that if we have a high tip speed ratio, it makes more sense to improve the use this friction reducing mechanism. And that makes sense too. And the first order analysis here, we can also figure out how much of the riblets we need to put on there. And for example, if we keep in mind that 75% of the power is produced in the latter 50% of the wing, and 50% of the power is produced in the latter 25%, this can give us a handle on, we can cover the rotor a much smaller percentage of the rotor and still get a reasonable effect. So we can also look at other kinds of windmills. Our lab is studying windmills underwater. Okay, so these are called hydrokinetic devices, and these are devices that extract power from flowing water, just like a wind turbine extracts power from flowing wind. And this is a model that's in our flume. We have a flume. This model is designed that the blades are downstream, and there's a long, complicated story on that, but this operates just like a wind turbine, except it's in water. And if you look on this thing, we can also calculate the power coefficient as a function of tip speed ratio, and you can see that there's an optimal here, and for this one it's around 6. So for this particular geometry here, the optimal tip speed ratio is about 6. So if we look at what we can do in the lab, you can see that we can study a lot of problems, but there are certain problems that we need to go to the field. We don't know. We know that the atmosphere is pretty iffy. It has all kinds of temperature fluctuations, velocity fluctuations. It's on a much different scale than we can generate in a wind tunnel, and we want to know how much stress is on the structure, etc. So for that reason, we call it the Helios field site, which is the thing you visited down at Umore Park. So that's illustrated here, and I'm going to just show you one slide here. So what the neat thing about this is there's the turbine, and upstream of the turbine we have an instrument tower. So we can measure wind speed and turbulence and temperature fluctuations. A whole bunch of things can be measured, and then we can relate that. Now, it also turns out that there's usually 2 significant positions that a wind turbine can produce. In this one, you can see that orienting that turbine in a north-south direction gives a maximum velocity, but then there's also a certain period of time where orienting over here, pointing to the northwest, gives results. Not as much wind, but certain periods of time, then you would get your best power output pointing into that wind direction. So we'll just look at this here. There is the velocity measured by that instrument tower. Okay, and that's measured up here at the hub height. Look at what happens to the turbine power. And that's a plot of the power coming out from that thing. And you can see that's quite a fluctuation. You imagine if you were in your car and you would just make the power fluctuate back and forth with the gas pedal like that. So this is quite a significant thing that has to be accounted for. And there's lots of things that go into this. And one thing that, don't get too nervous at this, we can also look at the wind, and we can break the component of those fluctuations up into frequency content. So this is a spectrum of wind velocity fluctuations, and we can do the same thing with the power. You saw that fluctuating power. We can also calculate how the power varies with frequency, And what's neat is we can actually calculate, it's a relatively simple thing to simply take the velocity and divide by a characteristic length, and that gives you frequency. So when you see a fluctuation, that fluctuation is induced by a certain chunk of turbulence moving by. Okay? So if you take that chunk of turbulence and divide by a velocity, that gives you, take the velocity, divide by the size of that chunk of turbulence, that gives you a certain frequency. So over the range of frequencies, we can calculate what the size of the turbulence is, and it turns out that most of everything is due to turbulence scales that are no smaller than the diameter of the turbine. Okay, this is the diameter of the turbine here, so that we know from that we don't need to worry about scales of turbulence that are smaller than the diameter of the turbine. Okay, and I won't go into this one. Oh, this one might as well do very quickly. One of the things that they did down at the U turbine is they actually instrumented it to measure the unsteady stresses that are on there. So that seems like a pretty obvious thing to do, but we haven't seen anybody else do it. So you just take the tower and put strain gauges all around the periphery of the tower, and those measure strain, which can be calculated to be stress. And you can see here that, remember that the maximum wind was pointing, if we pointed the turbine at 180 degrees, that's where we got our maximum wind. And you can see that's where you get the maximum stress if the turbine is oriented in that direction. Next thing I want to talk a little bit about is acoustics. And this is a very complicated topic, and so all we're going to do is just touch and give you a little bit of a flavor for this. Now, wind turbines are becoming more and more bad neighbors, if you want to think of it that way, because as they're getting closer and closer to built-up areas, some of the noise starts to bother them. Okay? When they're sitting out in the boondocks down in the southwestern part of the state and so forth, not bothering anybody, so you can't really hear them. But it starts to get to be a problem now, and much of what we know about wind turbine noise, it really comes from helicopter noise. Because helicopter noise has been around a long time, and there's been a lot of research going on in that. And of course, airplane noise and etc. has also been studied to death. So there's a lot of background and all of the primary physics that goes on to this thing. Now, we're only going to just talk just a few, give you a little essence for what the problem involves. One of the things that's really interesting is your ear and what a good device it is. If we look at sound, there's a huge range in power output. So, for example, the power output of a whisper is about 10 to the minus 9th watts, 1/1000th of a watt. And a rocket engine produces about 10 to the 7th watts. So there's a factor of 10 to the 16th. And I've not been to a space shuttle launch, but people that have been there told me it's just absolutely incredible. I mean, it just shakes your whole body. The noise is so extreme. Now, the other thing is that we're dealing with very small numbers here. So, for example, a 75-piece orchestra would produce about 10 watts. Okay? Even a 10-megawatt jet engine only produces about 10,000 watts. Okay? Very, very small amount. So about 0.1% of the power is produced as sound. And we have all kinds of different sound sources competing for our attention, so that also plays a whole psychoacoustic factor here. So if we look at the simple fundamentals, sound is nothing more than a pressure fluctuation, so that if we take the pressure at any instant, that instant is, we call it any position x, and that sound will vary sinusoidally, like so. Or if we keep time constant, the sound varies sinusoidally with respect to x. And the difference between, you can calculate how fast the sound is propagating by the difference in these two parameters here. And that propagation speed is called the speed of sound. And that speed of sound is given by the ratio of specific speeds, the gas factor R, and temperature. So it means that the speed of sound, as you go up in the atmosphere, the temperature is going down, so the speed of sound is going down. If we look at the product of frequency and wavelength, okay, wavelength is this parameter here, that product is the speed of sound. And we talk about the velocity fluctuations that are due to this, are this difference in pressure, which is already small, and it's divided here by the acoustic intensity. That's the product of density and the speed of sound. And we can talk about something called intensity, which is nothing more than the product of this pressure fluctuations and these velocity fluctuations. And that can be written simply as mean square pressure divided by this acoustic intensity here, rho times A0. And the sound power is simply integrating over the whole area of the intensity. The intensity is power per unit area, and so if we integrate over a whole area around, that gives us the total power. And we talk about the sound power level is simply we relate the power that's we're measuring to a reference power, or what you've pretty much seen is called sound pressure level, which is just equal to 10 times the log of pressure squared divided by reference pressure. And that if you work this out, this is just simply 20 times the log of this ratio of pressure. And how does that number vary? Well, if you went outside when they were working on the building over there, and if they're breaking up some concrete, the sound pressure level for the pneumatic chipper would be up around 140 dB. A rock group, not far behind, be about 120 dB. Auto horn is about the same value. If you go to the subway system in New York, for example, down around a little bit over 100. Conversation is somewhere, depending on the person, of course, but somewhere around 60, 70 dB. In the sound pressure level in a bedroom, a nice quiet bedroom, is typically about 20. And the way this scale is done, remember it's a pressure relative to a certain reference pressure. And so that reference pressure is picked to be the threshold of hearing. So 0 dB on this scale is theoretically the limit of your hearing ability. Okay. Now, that gets complicated because all sounds are not the same. And as you start to get older, you'll notice that your frequency response gets even worse. Okay. But this is illustrated here that if I would take the level that appears to have the same level of noise, so for example, let's take 40 here, and you notice that the actual sound pressure level that would give me 40 depends on the frequency. So for example, at around 3 kilohertz, 40 requires about 40, would be a sound pressure level of 40 dB. So 40 dB at 3,000 hertz, it would give you a loudness that's 40 phones, they call it, okay? But notice here that as you go down in frequency, okay, you notice here that you need to have a much higher pressure, sound pressure level, to get that equivalent loudness. So that low frequency, the equivalent loudness is less because the frequency is less. And the same thing is true when we go up in frequency. So the ear, as you can see, is most responsive at about 3 kilohertz. And your ear is less responsive at lower frequencies and less responsive at higher frequencies. Now this chart goes all the way to about 17 kilohertz, and that's for a young person, not a person like me. You find that as you get older, your frequency response gets much worse. Incidentally, another thing that happens is that you notice that you're most susceptible right in here, so that if you're exposed to a lot of noise for a long period of time, you'll start to get a notch in your hearing right at that point. I was a pilot for something like 44 years, and so I've got a notch in my hearing right around in here, simply from being exposed to all that noise of flying the airplane. And I've illustrated that here just to give you a feel for this. And here we're taking that loudness and converting that to how much loudness can you take for over a period of time. And that's these lines here. So you can see that if you had a very high sound level, of a huge, very loud, like 120 dB, you couldn't be exposed to that sound for more than 1.5 minutes. Okay? And as you go down in amplitude, then you can be exposed much longer. Okay, so the key question mark is here. I used to drive a Volkswagen, and don't ask me why I drove a Volkswagen for 7 years in this country. And it's the old Volkswagen, not the new ones that have a motor with a heating system in it. I drove the old Beetles. I don't know if does anybody know what an old Beetle looks like? Okay. Well, I drove one for 7 years when I first moved here, and that was crazy. But you can see that even for a Beetle, you're down, it looks like about 4 hours or so, you can be exposed to the noise of a Beetle going along. Now, this was a little schematic that was in the Trib, Minneapolis Trib 2 years ago, and it shows things in a very nice way here. It gives some idea of the various sources of pollution for these turbines. One is sound from the moving blades. Okay, another is the fact that you get a flickering, so that this blade is casting a shadow. So you can imagine if this shadow is going by you, and they're turning like just a couple of hertz at times. You could, drive you nuts after a while. And those pulsing sounds, that the shadow is going at that very low frequency, and same with the noise is pulsed at that low frequency. So, without going into a lot of detail here, if you would calculate the pressure that is due to a rotor, there's two components to it. One is the fact that there might be unsteady lift, so the rotor might be exposed to unsteady lift, like if it's in turbulent flow, it's not at a steady lift, but it's at an unsteady lift. And the other is the fact that the rotor is rotating, so that you have a component here that the rotor is accelerating away from you. You're constantly, accelerating, decelerating away from you. So there's two components here. One, if you had perfectly steady lift, you still would hear sound because of this component here. So that the rotation itself is going to give you sound. Now, the part that, on the first part there, the unsteady lift, that can be created a couple of different ways. And one way is that if you are having a rotor here and it's encountering a disturbance, that gives an unsteady lift, and that would give you noise. Another one is that even if the flow is perfectly steady, the flow, remember that we found that the flow goes from laminar flow to turbulent flow, and so at the aft end of that blade, the flow is turbulent. And it turns out that when that turbulence leaves the trailing edge, it creates a sound. And that sound has a directivity pattern that looks like that. And so you've got these various components of sound. You've got the sound created by the rotor passing through turbulence, sound created by the rotor just moving along by itself, and then you've got all kinds of other sounds that are due to other components of the machine. In this case, I'm showing a helicopter noise spectrum, and there's two noise sources. One is the noise component from the main rotor. The other is a noise component from the tail rotor, which is spinning faster, so it's at higher frequency. And then you can see this gearbox noise, and then finally down here, just noise due to turbulence. Now we have the same thing when we look at a wind turbine, it's got a very similar spectrum. The difference being that for a wind turbine, it's rotating at a much, much slower speed than a helicopter. So all the components that are due to the steady lift on the rotor, those components are at very low frequency. You don't hear those. Okay? What you basically hear is just the turbulence-induced sound. So the sound with the blade moving through the turbulence and the self-noise that's created by the blade just simply moving along. Now, the part that the blade is moving along is rather interesting. The reason for that is that its directivity pattern faces, if you looked at the rotor, the noise propagates to the leading edge of the rotor, not to the trailing edge. So the trailing edge noise propagates forward. So that means that if I would make some measurements on where the noise is coming from a turbine, this was done in somewhere in Scandinavia, the downward blade is making the noise. So the downward blade has got noise propagating down towards the ground. The retreating blade has got noise propagating up into in the air. So what you hear is the noise from the downward facing blade. And that's shown here on this illustration. This was out of this paper here. And so if I compare the two, as I said, the spectrum of a helicopter looks very similar to the spectrum of noise from a wind turbine. The key difference being that you can hear the helicopter rotor. You can't hear the rotor noise. What you can hear is just the turbulence-induced noise of the individual blades. Okay? So you can see the noise level is quite low. So what's the problem? If you can hardly hear these things, why are we complaining about the noise? Anybody have any idea? Well, how many people have been exposed to a dripping faucet while you're trying to sleep? Okay. Now, if you would take a sound level meter and measure the sound of that drip, 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 it's very, very low. Probably wouldn't even budge the needle, right? But you can still hear it. Drip, drip, drip. And that's exactly what is the problem with these wind turbines, is that they're not making much noise, but they're going zip, 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 and it just drives people crazy. So there's a psychoacoustic factor here that relates to trying to solve that problem. And it turns out that there's some things that can be done to control that, and we're working on those now. So that leads to, we got about 10 minutes left, 15 minutes left, and let's talk a little bit about flow control technology. Now, there are lots of things that we can do. We don't have to live with the way the turbine operates. We can actually improve its function to some degree. And one of the things we can do is do something using, this is passive control. These are vortex generators. How many people have noticed that on an airliner you see what looks like a bunch of little blades sitting up on a leading edge? Those are vortex generators, and they are there to improve the flow over the turbine. They mix the flow up and improve the flow over the wing of the turbine. Well, you can use the same thing on wind turbines, and what you actually use these to improve the flow, mainly towards the hub, where the foil is getting real thick, and the flow doesn't want to stay attached real nice, and you use these vortex generators and mix up the flow a little bit and get it to stay attached. Now, in addition to that, we can do what's called active control. So we can actually sense when the foil is trying to do something nasty, like have a load fluctuation or something. We can actually manipulate the flow to alleviate that problem. And there's lots of different ways to do this. This one is this is one example where they actually use a little piezoelectric ceramic here, and that gets a fluctuating flow coming out here, and that's called a synthetic jet. And if you position those at the leading edge of the turbine, you can actually control the unsteady loads that are trying to be created. Why worry about that? Well, turbines don't operate in nice uniform flow. There's lots of reasons they don't. Just see some examples here. The turbines in the back are not operating in a nice uniform flow that these are doing up here. You could have a unit behind a hill, etc. So you have all these components of inlet flow that are spatially and temporally not uniform. And those create unsteady forces. And, well, those unsteady forces can be disastrous. Here's a wind turbine that just totally collapsed. So the industry has tried a lot of different things, and they don't expect you to absorb this little table here, but there's all kinds of little aerodynamic techniques that have been tried. And for example, we showed you vortex generators is one. Blowing and suction is one that we've been looking at. One is a shape change airfoil. You know, the Wright brothers were the first ones to invent that they would warp the wings. They found that they didn't know how to get the thing to turn. And so they actually would warp the wings to create a rolling moment to get it to turn. And then you can see this, the synthetic jets is mentioned here. There's a whole bunch of other things. But you can see there's a lot of different things have been tried. Now, we've been working with Syracuse University on this problem. And they have a very wide background in looking at active flow control for lots of different cases. One case is an airfoil of an airplane. Another case is this is actually a turret that's on an airplane that collects information, and the flow over it is unsteady, and they use suction to actually improve. You can see here's the flow without the device turned on. Here's the flow with the device turned on. You can see how much smoother it stays. And they've been looking at using synthetic jets, for example, to reduce jet noise. So in our case, what they did was they've taken our foil, which in our wind tunnel is 1 meter in length, and they don't have a facility that can handle a 1 meter foil. So they have a 1/4 meter foil that is instrumented. So it's instrumented with pressure taps. It's instrumented at various places where they can blow air in to control the flow at 10, 50, and 85%. In order to, since the foil is relatively small, only a 1/4 meter compared to our 1 meter foil, to make it look like a foil of operating at higher Reynolds number, actually tripped the boundary layer right here with a tripwire. So they have this foil, and they have it instrumented. And what they can do is they can sense unsteady pressure, and when the unsteady pressure is happening, they can blow air in there and control that flow and actually snuff that out, provided they phase it correctly. And so, of course, there's a control algorithm that has to be used to do that. But they actually have already gotten some reductions in unsteady lift of the order of 10% already. So that's pretty good. And that's just the very beginning. They haven't really done much more with that at this point. And that's with a relatively small amount of flow to control it through those jets. So what I've done is I'm finishing, 7 minutes early. I don't think anybody will get mad at me for doing that. And what I've done is in your package, there are some references, and I want to point out one of them here. It's this one here. It's not wind energy for dummies. It's not down to that level, but it's a very nice one. And actually, it was on sale in Amazon. And what the crazy thing was that the paperback version of it in Amazon was $130, and the hardcover version was $70. So guess which one I ordered. Don't ask me how that happened, but so for $70, the way textbooks are going these days, I think my tuition when I first started school was about $70. But So $70 is relatively cheap for a textbook these days. But anyway, so I gave you a list of references there, and 3 of those references are reprinted in your packet. This one, for example, is out of the annual reviews of fluid mechanics a year ago, and that has some very nice information in it. So that's about it. I've tried to be selective in these references so that if you want to dig more deeply into it, you can do that. The homework problems are relatively straightforward and simple because I figured there's just no way to give you nitty-gritty problems with such a limited exposure to the problem. So with that, I'll finish. I'll be happy to entertain any questions that you might have.